Have a good one.
Yeah.
Thanks, mate. Bye-bye.
Well, thank you again for the introduction and the opportunity to speak, David, and thank you everyone for joining. So as David mentioned, I'm going to be talking about friction-free online shopping with Signifyd, how we use data science to take calculated risks to improve the global state of e-commerce. There we go. So just a little outline of what I'm going to talk about today. I'll just start out with an introduction to Signifyd and who we are as a business and what our business problem that we tackle is. And then I'll go into fraud in more detail and how we treat that as a data science problem. And then divide that up into some sort of the core parts of data science, feature engineering, modeling, and decisioning. So who are Signifyd? We are the world's largest provider of guaranteed fraud protection, enabling e-commerce retailers to provide friction-free buying experience by shifting fraud liability away from merchants. So there's a lot of payments and e-commerce jargon in there. So let me try and unpack that a little bit more for you. So for online retailers, the fraud problem is quite acute, or is more acute than many people would realize. So first, to set it in context, I think everyone will be aware that e-commerce has been growing very rapidly over the last few years, and in the last year in particular, we've seen a huge explosion with the pandemic shutting down large areas of in-person retail. We've seen the growth we were expecting to see over 5 years in a couple of months in 2020. And in the UK in particular, 2020 saw a 36% year-on-year growth in online retailing. So online is clearly here to stay and is becoming vitally important for all retailers, not just those that were originally considered or would have traditionally been considered as e-commerce retailers. But something I think is probably not well known outside of payments or e-commerce circles is that retailers are liable for fraud in e-commerce transactions. So in any transaction where your card is not physically present, so that could be internet shopping, it might also be telephone shopping or something like that, or I guess even shopping by post. I don't know if anyone does that anymore, but the old catalog sale type model. Those kind of transactions, the retailer takes liability. So if the cardholder reports that a transaction, they don't recognize it, it wasn't them, it's up to the retailer to demonstrate it was the real cardholder making that transaction. Otherwise, the cardholder's bank will reclaim the money from the retailer's bank. So this is a problem for retailers because they're not really, they're not fraud experts. They're not in the business of identifying good orders and bad orders in a fraud sense. You know, they're experts in deciding what people, choosing what people want to buy and marketing that and encouraging as many sales as possible. So when they realize they have a fraud problem or they're liable for these chargebacks, they tend to either go down one of two routes. Either they will decline too many orders because they're not fraud experts, and they're being overcautious, or they introduced high friction anti-fraud measures, which kind of drive away genuine customers because it's too frustrating to get a purchase completed. So let's just dive into a little bit more how that fraud picture might manifest itself to the retailer. So on day one, we have a purchase is made, but unbeknownst to the retailer, some stolen financial information is used. So there's a whole market on the dark web of stolen credit card information, and you can, if you know where to go, you can go and buy tranches of stolen data. And some of that has complete information, the full credit card numbers, the CVV numbers, billing addresses, everything. But the merchant is probably unaware that this is stolen information and will ship the product out. So sometime in the next 90 days, which is the typical window that the cardholder has, the cardholder will notice the transaction is fraudulent. There's a transaction on their account they don't recognize, and report it to their bank. So 90 days is typically the window that you have to report a fraud transaction on your account. So once that report is made, the cardholder's bank will reclaim the funds from the merchant's bank directly, and the presumption is in favor of the consumer in this case. So it's the the merchant loses the money, and then they later have an opportunity to contest it. But as soon as the chargeback is filed, the merchant loses the money, and they're out of pocket. So the merchant can go on and dispute the chargeback, but that turns into a really complex and lengthy process. And to be honest, most retailers just chalk that up as a loss and move on. So how can Signifyd help with this? Well, we see ourselves as the fraud experts. We think that merchants shouldn't have to worry about fraud. They should outsource their fraud problem to someone like us. And we can help them maximize their revenue and maximize conversion as well. So we will help them to accept more orders because we work with retailers around the world. We have a global network of data that we can use to allow us to accept orders others would view as too risky because they don't have such a broad picture of what good transactions look like. And at the same time, we will minimize false declines so that we maximize the revenue you're getting. Our solution is built on machine learning, and so we can automate large fractions of the order review process. So this means we'll have much faster checkout confirmation, and lots of businesses will be able to relocate their in-house fraud services to us so they can reduce their in-house costs that way. And finally, we are confident in our solution such that we'll give 100% financial guarantee. So anything that we approve as approve for dispatch, if there's any chargebacks that result from that, we will cover the financial loss that the retailer suffers. So everything that is a guaranteed sale, guaranteed by us, the retailer can count as revenue. There's no chargeback losses to consider in the future. So this has been a really good proposition for lots of retailers. We have over 10,000 customers now, and we work around the world, over 100 countries throughout the Americas, Europe, and Asia Pacific. And to date, we've guaranteed over $30 billion of merchandise. So just to put a little bit of meat on those bones of what we do, a couple of examples of retailers that we've worked with. So Samsung is obviously a well-known electronics retailer, and they have a direct-to-consumer website. They have a previous fraud provider who is declining too many good orders, and also there were very long decision times, which frustrated customers who want to get their hands on these new electronic devices as soon as possible. So we worked with them and increased their conversion rate by 10%. We've gone to 100% real-time decisions, so no human review. And for those chargebacks that did arise, we have improved their win rate on disputes by 50%. Another UK-focused example, Emma Mattress. They had a fairly low fraud rate historically because they used this 3D secure anti-fraud workflow, which you may have seen pop-ups that come up sometimes when you're buying something online, which redirect you to a bank website. The 3D secure is good for preventing fraud, but that introduces friction, which leads to a lot of customers abandoning their checkout. So we've managed to remove that step and increase their orders accepted by 6.5%. Of course, they are suffering no fraud losses because we cover any that occur, and they've achieved a 12 times return on investment in the first 2.5 months. So that's just a glimpse at how Signifyd fits in the e-commerce world, where we fit in the marketplace. So I'm now going to dive into what decision science or data science within Signifyd does. And I guess the simple answer is that we come up with the way of identifying safe transactions at purchase time while preventing fraudulent ones. And there's a few challenges that we face right at the start for turning this fraud problem into a machine learning problem. The first problem, which I guess is a good problem for the world to have, but makes it difficult for us, is that fraud is a very imbalanced data problem. About 25 pence in every £100 we see is fraud. So it's good for the world that there's not too much fraud around, but it makes it hard for us to build models when the thing we're trying to identify is very rare. And it's doubly hard when you think about the kind of rareness you're seeing here, is that the what I call the long tail of good orders look quite a lot like fraud. So if you think of the kind of things that you might expect a fraudulent order to look like, if someone's stolen a credit card, they'll probably try and buy as much as they can while the credit card's still working, for example. But that kind of behavior, what we'd call high purchase velocity, that looks a lot like a power buyer, like someone who is a secondary seller, or maybe who owns a business and is ordering lots of parts for repairing equipment or something like that. They might be ordering lots and lots of things every day as well. And then there's things like, we'll see later in the presentation, one of the tactics fraudsters use sometimes is to manipulate addresses or email addresses to try and circumvent our fraud detection purposes. But there's plenty of honest typos in genuine orders. People, typing on their phone, people misspelling words, accidentally putting things in. So, and the frequency of these honest typos can be much higher than the frequency of sort of adversarial attacks. And the final example I put here is holiday purchases. So something fraudsters sometimes do is get things delivered to hotels because it's easier to, they don't need to physically go there. What they do need to physically go there to get the purchase, but they don't need to be there for very long. It's hard to track down who actually picked up that purchase. But of course, genuine customers sometimes are staying at a hotel and want to order something to their hotel. So this is a problem for us, the imbalanced data target, and I think it's more of a problem than you might think in a sort of abstract machine learning sense. It's more of a problem because of this long tail of good orders as well. The next problem we have is our incomplete target information. So if you think about how I described the fraud, how the fraud process works, we get fraudulent. We know things are fraud because the cardholder reports them as fraud. But if we start declining lots of orders and they never get sent out, and that there'll never be a charge on someone's credit card statement to dispute. So we only ever find out things are fraud for sure if we approve them. Orders that we decline, we won't find out the true outcome of those. So there's an incomplete target information. And then there's also a problem with a kind of noisy target information. So it may have already occurred to you that if all you have to do to get the money back for a purchase is call up your bank and say, this wasn't me, that this process is open to abuse. And indeed, customers do abuse this. People will make false chargeback reports in an attempt to get things for free. And while there is a process, as I mentioned, for disputing chargebacks, it's lengthy, it's somewhat expensive, and it's not always successful. And so there are items in our data, in our order history, which are labeled as fraud, but which are in reality were the real cardholder who's got away with abusing the chargeback process. And then finally, and I guess most obviously in a way, our target is an adversarial target. It's not like if you're modeling something like maybe in fire risk for houses or something, where your target is fairly static over time. Houses aren't actively trying to catch fire. It's just a rare event that happens. In our case, fraudsters are actively trying to circumvent our model. They're actively trying to get around the filters we put in place. And once they find a way around that a particular model, those details are likely to be shared online with other fraud rings, and they can be quickly exploited. So there's never going to be a time when our fraud model is done and finished and we can all go on holiday for a year. We're always going to have to be refining and improving our approach, because the fraudsters are always trying different methods to get around our model. So with that in mind, the key decisioning techniques that we use within data science team are obviously machine learning. So that's the core of our solution and provides most of the decisions. It's fast, it's highly scalable, and it's very accurate for the most part. But we do have to supplement machine learning with a few other techniques. So we have merchant-specific rules. So these are just procedural heuristics, if you like. And these are important because they can be very rapidly deployed, and they can also implement sort of business policy rules. We sometimes implement on behalf of retailers. So things like what you might class more as customer abuse rather than outright fraud. So people placing too many orders in a promotional period or something like that. And then finally, we do use expert risk analysis as well. So this is used for both for model supervision, so kind of overwatch of our model results and checking that there's nothing untoward going on. There's no egregious outliers that where our model has done something odd. They also use for very high value transactions or transactions where the model is very uncertain of the result. We have some human, so I guess you could call it like human in the loop AI, where we're using human decisions to augment and improve our feedback loop. So our overall machine learning pipeline looks something like this, and I guess it's a fairly familiar supervised learning problem for anyone who's dealt with this kind of problem before. So everything starts at the left here with our order data, and that goes into our feature engineering pipeline, where we turn kind of raw data points into, we kind of enrich them and turn them into numbers which tell us something about the fraud-like nature of this order. We then take those features into model development and build machine learning models with it, evaluate them offline against, and if the performance is insufficient, we'll go back to feature engineering and repeat this loop a few times. Once we have something we're happy with there, we can go ahead and deploy the model, start decisioning live traffic, and those live models are also evaluated. So we're doing A/B tests, online loss rate evaluation, human feedback, as I mentioned, and some anomaly detection to try and catch any anomalous spikes in traffic, either anomalous spikes where we're suddenly approving much more than we expect, or anomalous declines where we're suddenly declining more than we expect. This thing feeds into what is kind of rather jargonly called business goal optimization, but basically means turning the model prediction, like a probability, into a decision, so a guarantee or decline. And then finally, we pass through our rules. So I'm going to talk about each of these stages in a bit more detail now. So everything starts with the features, and we have this saying we like to say: models will be as predictive as the features are expressive. And by that we mean we want to not just put the raw data that comes into our shop into the model. We want to try and combine it in ways that we know are predictive of fraudulent behavior or safe behavior. So so we make a lot of use of our in-house risk experts to tell us in the data science team what fraudulent behavior looks like, and then we work out how we can encode that in features. So we use internal data. So we use the data that's sent to us from the merchant, our internal data, and also third-party databases. So to give you a few examples of what fraudulent transactions might look like and the kind of things that we look for, I have a few examples for you here. So this is a fraudulent transaction, and the first thing you might notice is that the item are these high-value tools. So it's not completely clear from the names of these items here, but we know it's a tool retailer, and there's some kind of electronic measurement devices here, and they're a couple of $100s. So these are expensive items, and we know that tools have high resale value. There's a big secondary market for them. So that's the first kind of risk factor. This is a risky transaction. The next thing we notice is that the billing address, which is represented with this credit card here, the delivery address, and the IP address where the order was made from are all quite well separated, a few hundred miles apart. Now that in itself is not, it's not In itself, that's not something that would make us block the transaction, because there are genuine reasons people order things to be delivered not to their billing address, and they order things when they're not at their billing address and not at the place it's going to be delivered to. However, it is a risk factor. If you're a fraudster, you're going to get something delivered not to the cardholder's address. So this is a risk factor, and combined with the final risk factor would lead us to decline this transaction. So the final thing we'd notice is that across all merchants, we've never seen an order from this particular email address before. So if we had an order history and we'd seen items previously being delivered to this delivery address, for example, and no chargeback history associated with that, then we could be more confident that this was an okay order. But as it is, with risky items ordered, this big separation between these three, the addresses and locations we have, and no good history, this order is too risky to approve. Next example here is a set of 4 transactions. So each of these rows in the table here is a transaction, and there's a few details about each transaction. So the first thing to notice here is that there's 4 transactions placed within 90 minutes, and they're all for high-value smartphones. So that's pretty unusual. Most people would buy a smartphone, once every couple of years, maybe. Buying 4 in 90 minutes is very unusual behavior. The next thing to notice is that the email address kind of looks weird. It's like someone's name. There's like a bit of someone's name here, Murray, and then something else. But there's a lot of random periods peppered throughout this email handle. And that is, again, a risky, sort of suspicious email handle, we'd call it. It's often a tactic fraudsters will use to try and circumvent our order history matching, is to put superfluous punctuation in identifiers. The hope being that we will sort of a naive pattern matching wouldn't match this to previous orders. And in this case, the email provider it's from is normalizes email handles. So these periods have no effect on where the email is delivered to, but they would impact any kind of naive literal string matching that we did. And then the final thing that's weird about this order, suspicious, this email handle has no relationship to these delivery recipients. You can see it's Raymond and Joshua, and that it's not reflected in this name. And I can tell you that the surnames also were not reflected in that email handle, and also that they're made. There's 2 different delivery recipients. So even if this was, if the one way this might be a genuine transaction is it's some kind of power buyer, some kind of reseller or something could potentially be buying multiple smartphones, but they wouldn't have them sent to different delivery recipients. So that is unusual. Okay, and one final example for you. This is a transaction which is going to I can tell you the address it's being sent to here is a reshipper in Miami. So this is somewhat, so a reshipper is like a freight forwarding company that you can send a parcel to, and it makes it easier to send things internationally. And the order is being placed from an anonymous proxy, and there's a sort of meaningless username here, which is just a string of basically a random string of letters and numbers. So this looks risky, right? Anonymous proxies are always risky, and arbitrary strings as usernames are risky. However, something which is not shown here is the recipient's name, which is a Chinese name. And in the context of that, it's actually not. We don't view it as risky, because lots of Chinese buyers are more or less forced to use proxies in order to access Western e-commerce sites from the internet within China, and they often pick email handles that look somewhat meaningless to us, because they're not really very familiar with the Latin alphabet. If you imagine if you were forced to choose a username in the Chinese alphabet, you might, the characters don't really mean anything to you, so you're likely to just pick a random string of them. So in the context of this order, we'd actually say the anonymous proxy and the string are not risky. However, what is risky is that the bank that the card is registered to is registered in Mexico, and that is very suspicious, and that would cause us to decline this order. So that was like a bit of a whistle-stop tour, and it may have been hard to see all the features I was picking out on those slides, but I hope what you took from that is that there's a lot of different things that might be risk factors, and it's very context dependent, and that there's no one feature which will tell you something is fraudulent or not. It's about evaluating them all in context. So with that in mind, we try and build as broad a set of features as possible, with everything that might give us information about whether something is good or bad. So we can categorize the features into a few different classes. So the first set I would call identity features. So these are things that are picking out pieces of information which identify the individual or a group of individuals. So, for example, the email, the phone, address, payment instruments, and we use all these pieces of data combined with the returns from third-party databases that tell us about them. And then we also look at behavioral features. So we get some information about the way the user interacts with the website. So that can include things like typing speed, mouse tracking, time on pages, time to check out, things like that. And the insight here is that the way a genuine shopper behaves on a website may be quite different from a fraudulent shopper. A genuine shopper tends to look around, choose what they're going to buy, consider purchases, maybe look at the return information. A fraudulent buyer is more likely to know exactly what products have the highest resale value and go straight to those and buy as many of them as they can. Also, of course, there may be bots involved, and bots look a bit different from humans, particularly in typing speed and so on. Another feature class is device features. So we get information about the device that's being used, and that helps us both to see whether they're using an unusual device that maybe is a virtual machine or something like that, but also allows us to create fuzzy device fingerprints. So by hashing a combination of lots of different characteristics of the device, we get a sort of pseudo ID for that device, and we can then link orders that have been made from the same device, or probably the same device. And then finally, and probably most importantly, we combine all of these features together across our network and across the history of orders that we have from all our retailers. And that greatly improves our power, because as I've said several times now, it's all about the context of the order. And while it might be unusual for me to buy 4 smartphones in an hour, there's probably specialist people who are always buying smartphones, and for them it's completely normal. So if we have history features that, for example, identify the average amount I spend in a day, or the Z-score deviation from the mean of my purchase a day and my average purchase in a day, these kind of things can really tell us whether this transaction is unusual for this user, for this address, for this device ID, for this country, for this merchant, so on and so on. So this is really where a lot of our power comes. And for that to work, it's important to have a good network coverage, and thankfully we do. We have fairly well balanced coverage across the globe now. We're still somewhat preeminent or dominated by the Americas, which is where the company was founded, but we do now 36% of our traffic is from Europe, and 20% from Asia Pacific, and 98% of the transactions we see are identified by at least one of these variables to link it to a previous transaction. So features, as I'm sure everyone who's worked on machine learning knows, features are key. It doesn't matter what algorithm you use; if you don't have good features, you'll never make a good prediction. And it's what we spend an awful lot of time on, updating, developing our features to develop to catch new fraud trends. So I thought I'd do a little kind of case study of a recent bit of work we did on what we call gibberish address detection. So the aim of this is to try and identify character sequences in addresses that have been manipulated or are meaningless. So we saw in that fraud example, the email handle that had random periods shoved in it. We see a similar kind of pattern with delivery addresses sometimes. So here, for example, the real address is 8372 Northwest 68th Street, but the fraudster has put in some random punctuation and abbreviated some words. So their aim here is that we will, if we were to do a naive address matching, we would not match this left address to the right address, and we would therefore, the fraudster hopes, not associate this delivery address with the bad fraud history of this delivery address. However, he's also hoping that the postal worker will see this and correctly figure out that the parcel should go to here. So we would like to be able to detect this kind of adversarial attack. So one way we've tried doing this recently is using a Markov chain model. So a Markov chain is a way of describing a sequence of possible events where the state of each event only depends on the previous event. So in the context of character strings, which is what we're dealing with here, each character we consider like a single event. And then we build a model from this by using, it's like an unsupervised method where we'd use just good examples of character strings, and then use that to generate a transition matrix, which will enable us to give a score for any new string of how likely it is to emerge. So for example, there's a little bit of a tiny amount of maths on the right hand side here. So if our corpus only consisted of the letters A and B, we might come up with transition probabilities like this. So A to A is 0.3, A to B is 0.7, and so on. And then this would allow us to calculate the probability that this string ABAA emerged from the same distribution as the training distribution. So we tried this on US addresses using 69 characters. So that's alphanumeric characters and then the common punctuation marks that we see. We trained that on a large number of approved good orders. So that means orders we approved and for which we got no fraud reports. And the output of that is our transition matrix, and that enables us to calculate a quality score for new addresses. So any new address we get, we can come up with this number based on the transition matrix of how likely it is to be appear basically in this corpus of good orders. We evaluated that on a bunch of orders, of approved orders, but this time we included fraudulent orders. And we see results that look a bit like this. So on the x-axis here, we have quality score. So as we increase in quality score, these things are looking more like the addresses we saw in the good orders. And at low quality scores, we see a much higher fraud rate. So this is basically saying that I've written the x-axis the wrong way around, but it's fraud dollars over approved dollars. So for very low quality scores, we see almost 30% fraud. So in a univariate sense, this feature is doing very well at capturing fraudulent orders. But of course, it may be different in the model. When we added this as a feature, just adding this feature to a model gave us a 1% improvement in loss rate, which is, it's a modest improvement in loss rate, but in general, a kind of rule of thumb we would use is that we look for a 10% improvement in loss rate to launch a new model. So this single feature has got us a tenth of the way to a new model. And I'm sure there's lots of ways to strengthen this feature. So we could extend it to other string-based items in our model. So for example, cardholder names, emails, and so on. And we could also look at using, rather than using the whole address, use substrings, and also possibly go from single character transitions to multi-character transitions. So there's ways we would probably improve this. If you can think of more, then you could apply for the job and come and help us. Okay, so that's a little insight into features. Let's move on to the model development stage of things. So our model is the model we use is XGBoost at the moment, but the model we end up with is a combination of the algorithm and the features. So we combine the XGBoost algorithm with our 10,000 feature catalog, feature catalog of 10,000 features, and do some feature selection to whittle that down to around 1,000 features typically. In order to use any kind of model, any kind of supervised model, we need to know what our target is. And I've kind of skated around this issue so far, so let's explain that now. So the clear goods, what we have is our negative class, our zeros, our approved orders with no chargeback information. So they're approved orders that are older than 90 days and have no chargeback. The clear bads are those approved orders with fraud chargebacks. And then we have a kind of gray zone for these declined orders. So as I mentioned earlier, we don't know the real outcome for these. We can't just remove them from modeling. If we were, that would be the easiest thing to do. But if we didn't include these declined orders, then it would be like it would be like each new model was completely forgetting what the previous model knew. Or if we removed all these declined orders, then the new model would only see the orders that the previous model had approved. And that's no good, because we have faith in our model. We know the previous model was doing something right. It was doing something right. But equally, we can't include all of these declined orders, or at least we can't include them in the same way as the bads, because then we just end up in a spiral of ever more conservative models, because the new model you're training would consider declines as just as bad as clear bads. And while while as I said, we have confidence in our model and we think we have a low false positive rate, we are not so we are not so unrealistic as to think we have 0 false positives. We know there are some orders in this gray zone which probably were genuine orders which we declined. And so the way we get around this is we weight the orders differently. And there's a lot of different things we use to determine the weights, and I'm not going to go into all the details, but you can think about the different ways, different order amounts, different ways that we decline them, by model or by manual review or by rules, and those are the kind of things we use to derive the weights. But there's a lot of work to be done on weighting schemes, and it's one of these I guess one of the kind of corners of machine learning that in some ways is more like a craft than a science. There's more than one way to skin a cat in that department. Once we've trained a model, we obviously have to evaluate it. And the key evaluation metric we use when we're training the model and optimizing hyperparameters and so on is the area under the ROC curve. So this is an ordering metric. So it's saying something like, are those orders with a higher score more likely to be fraud than those with a lower score? And that's very useful to have a single metric like that for grid searching and choosing of parameters for your model. It also works quite well with an imbalanced data set, which, as we mentioned, is something we suffer from. However, it has the drawback that it considers all chargebacks equally bad. So when we come to actually evaluating what our models mean for our business and for the businesses we are working with, we use a different set of metrics. So the first one is the loss rate, and that's the sum of the chargeback loss divided by the total value that we've guaranteed. And that's our key metric at Signifyd, because if this loss rate is too high, we won't make any money and we will not survive as a business. For our merchants, the key thing that they like to know about is the approval rate. They want to know what fraction of transactions that they sent to us they were able to send out. And you can see there's a very clear trade-off between these two. We could have 0 loss rate if we approved nothing, but obviously our customers wouldn't be very happy. So yeah, these two things kind of trade off against each other, and we have to work to keep both sides happy, basically, to make sure we have a loss rate that we internally are comfortable with, but an approval rate that our clients are happy with. And I should say actually as well, I don't think I mentioned earlier, but our incentives are aligned to give them a high approval rate. So we generally get paid per order. So if we approved no orders, we wouldn't have a loss rate, but we also wouldn't be getting paid anything. So it's in our interest as well to have a high approval rate. And I guess it should be obvious, hopefully, that in order to get these metrics, loss rate and approval rate, we have to convert our model scores into model decisions. So that's going to be the next section. I'll explain a little about how we do that. We start off with a machine learning model, and I call this a prediction. So I guess what I mean there is this number between 0 and 1, which is something like a probability where 0 is not fraud and 1 is fraud. And then we push that through a set of thresholds. So that's just a set of conditions where we say if this particular order, if its score is below a particular number, then we will approve it, or if it's above that, we'll decline it. And that gives us a provisional decision. And the provisional decision might be guarantee, decline, or manual review. So as I mentioned, we have these these fraud experts in-house who do a human review of some orders. And then the provisional decisions are subject to rules. So as I mentioned earlier, there are some, we have a rule set, we have these heuristic rules that operate on top of the model, and they can overturn these provisional decisions. After it's been through rules, anything that's still flagged for a manual review, a human will have a look at. And then finally, everything will end up with a signified guarantee or decline. So thresholds look something like this. So this might be our score distribution for a set of orders. So on the left here, we have low model scores. They're less likely to be fraud. High model scores, more likely to be fraud. And I hope you can see that the graph here, you should note it's a log scale. So there's a lot more, 100 times more good orders down here than there are bad orders over here. And you can see there's a funny little peak at high fraud scores, because there's some absolutely terrible orders where we're 100% sure they're fraud. So we get this spike at 1, and then a kind of gray zone in the middle, and then lots of very good orders where absolutely everything ties. So the question for thresholds is where should we draw the line in here? Where should we decide to approve above and decline, sorry, approve below and decline above? We might decide it's there. And basically we do a lot of scenario testing to work out where this line should be drawn. That might be where we draw it for low value transactions. For high value transactions, we might draw them more like this. So we have a smaller approve region, a larger manual review region, and a larger decline region. So obviously, as transactions get more valuable, it becomes more worth our while to have a human spend some time looking at those orders. And then once the thresholds have been applied, we have this set of rules that we can apply, or that the case goes through. So these are what we'd consider them our kind of our firefighting tool. We use them for instant clampdown. The model development cycle typically takes, probably a month from deciding we're going to build a new model to going through all the steps to getting it deployed at some level. But when a fraud attack hits us, we need to move in hours. We can't wait a month to stop this fraud, surge of fraudulent orders coming in. So the rules allow us to do this using basically any feature that we have in our feature catalog, and then plus some kind of meta model properties. So for example, we could say we could base a rule on some features, and also the model score has to be greater than X as well. To give you a recent example of when we had to do this, just last weekend, there was a kind of a fairly bizarre incident where a social media rap star posted a video saying, hey, there's a credit card hidden in my video, try and find it and buy yourself some pizza. so quite a lot of people found it. They didn't buy pizza. They went on various merchants that we work with and placed thousands and thousands of dollars worth of orders. So we had to instigate a rule which identified those orders by the card bin and last four. So basically the first 6 digits of the credit card and the last 4, and blocked all orders just based on those properties. So we can do that and deploy the rule within minutes, and then we're safe from that kind of fraud. Okay, so I'll quickly go through this because this is probably the less interesting part of the talk, but just to give you a sense of the toolbox that we use within Signifyd for data science. We have an in-house model training orchestration platform called Veda, and that's built by in-house and supported by the in-house engineering team. And that just makes our model building pipeline reliable, repeatable, and we can, everyone in the data science team is doing the key stages of the data science pipeline in the same way. So we have a nicely reusable pipeline there, and we know that we're comparing apples to apples. For our ad hoc work, we're using Python and Jupyter notebooks, and we do that typically in Kubeflow. So this is a kind of cloud-based system. So that really works for us because we have seamless access to our data from there. And it's also easy to share notebooks within the team. So you can point your colleagues at like a live notebook, and they can look at what's going on there. But also it has access there to our Git repo. And so any tools that we're building, we can commit to the Git repo. We can have the good code governance around that, code reviews and unit tests and so on, and then make these little sort of mini Python packages accessible to everyone else from that area as well. And finally, the production features, they live in the production code, which is owned by the engineering team, but we like the data science team to implement them us directly because that just speeds up the loop of feature development. It means we have, there's not so much communication bottlenecks where we're trying to explain to the engineering team in Jira tickets what we need them to do. We just go and do that. So that's really good. We have kind of full control of our features. So we can be very responsive there. And finally, as Dave mentioned at the start, we are hiring. We're growing very quickly in Signifyd, and we are hiring in Belfast. So we're looking for either in person in Belfast at our R&D centre here, or we'd also consider UK remote. So if you've been interested in what we talked about today, please do get in touch with me or Steph, or you can find our details on LinkedIn, and we'd be happy to talk to you more about what we do. Yeah, thanks for listening, everyone.
Perfect. Thank you very much, Rob. What an interesting challenge. So yeah, I absolutely loved hearing about it, and it's clearly a constantly moving goalpost as well. So I'm sure you've got your work cut out. One thing I'd just say, if you are watching at home and you did enjoy that, if you wouldn't mind just sticking a little thank you in the chat, it's quite nice for the speaker just to realise that there are hundreds of you out there watching at home, and it's a bit of a virtual round of applause, which is always quite nice. We will jump into the Q&A now. As expected, we've had quite a few questions come in. We've got 13 there at the moment. They can be upvoted if you see a question that you particularly like the look of. I think I've probably got 7 or 8 questions of my own as well, actually, Rob. So luckily, we're probably not going to have time to get to my questions, and we'll start with the people that have been watching along at home. So we'll start with the top. If you open the Q&A at the same time, Rob, it's quite nice just to read along at the same time. We will start with that top question there from Alex. How do you conduct A/B tests with such low volumes of fraudulent transactions?
So we have low volumes of fraudulent transactions, but we still have. So I guess we have a low fraction of fraudulent transactions, but we see sufficient numbers of transactions that we still see enough transactions to do A/B tests. So yeah, we maybe have to run the A/B test long. I don't know what other, I guess maybe industry norms are different. Maybe if you're doing, maybe if you're optimizing something in Amazon's web shop, you might run your A/B test for a day or something. We typically run them for a couple of weeks or more to get enough data to do it. Okay. So we have low, I guess we have low fractional fraud, but we still have enough, we have high traffic levels. So we see enough to do an A/B test. And we're normally not, well, luckily we refresh our models often enough that it's not normally critical to change model. We're just refreshing, updating, and we're happy to have 50% of traffic, say, going to the old model, while that's okay. It's not, the loss rate's not tanking so much that we have to change now.
Understand. And what sort of improvement are you looking for? Are you talking about, a fraction of a percent improvement makes a big deal to your models, or are you looking for, really for the big wins, or what looks like good in terms of improvements?
So I always find it a little confusing, because there's two things. There's you'll always get, our models go stale relatively quickly. So if you keep the same model for 6 months, the performance tails off quite noticeably, and just retraining that model with new data will bump the performance. But I think we'd look for, I think I mentioned a kind of rule of thumb is something like a 10% improvement in loss rate. And it can be hard to, the AUC, it doesn't always tally with that, but a decent jump in AUC, a few percentage points in AUC would be good to go with that.
Okay, but fantastic. Thank you very much. We'll go to the next question down on that list. It's coming from Nick. Nick's talking, I guess, a bit about data protection rules and stuff like that. He notes that you're using end customers' email addresses and attributes. Are you having to use a one-way hash to meet data protection legislation? If so, how are you doing it? If not, how do you deal with GDPR? So yeah, I guess there's a few questions that have come in, I guess, around how you guys manage data and data governance and stuff like that.
So yeah, as you've seen, we do use the raw datas, and the raw datas. We do use the raw email addresses and things like that, like custom identifiable data. And I believe we have, because we are fraud prevention usage, we have various exemptions that allow us to do that. So we do have obviously compliance teams and things who pay close attention to that, and I wouldn't claim to know all the details, but I'm assured that we are operating within all the relevant legislation, and it's thankfully for us, there are exemptions that enable us to do this because of the use case that we have.
Interesting. I wasn't aware of that, but it makes a lot of sense, and you answered that perfectly. Any questions about compliance, it's always good to slightly swerve. Also, raw datas we're always looking for ideas what to print on t-shirts and stickers and stuff like that, and raw data could become our new saying, our new catchphrase. Next question that's come in there, it's from Alex. For your gibberish detection model, have you tested in multiple languages or just testing against US English for now? Is there a way for using it in other languages that have the Latin alphabet?
Yeah, that's a really good question, because obviously addresses are, well, not only is the language they're written in going to affect the character distribution, but the whole format of addresses is different in different places. So it's definitely going to, the thing I presented today is definitely a localized US model, and we have looked at, we do look at it differently in different geographies. So particularly, we've been expanding in Latin America recently, and things are definitely quite different there in terms of both what addresses look like, also what people's names look like. There's quite a strong norm in Latin American countries for everyone to have 2 surnames that they use at all times, so that kind of thing is definitely localized, and we have to be conscious of that and work out where to be local and where to be global.
Perfect, thank you. And that actually leads into one of my questions, and I guess as the host, I get to ask one of my own questions, don't I? Surely there's got to be some perks. It was more in terms of fraud patterns. I mean, do you see different patterns of fraud in different countries?
Yes, I think so. So unfortunately, I hear from the team that works on the Latin American problem that stuff is very different there, and the fraud, I think in particular, it's just like the baseline fraud rate in some of the countries they've been working in there is just a lot higher, and I don't know why that is. If it's just yeah, I guess I wouldn't really like to speculate what all the different kind of societal effects are that mean that's the case, but the baseline fraud rate is a lot higher, and so that's definitely been a challenging market to enter, because the base fraud rate is much higher, and before we entered that market, most of our history was in other markets. So it's quite challenging to launch models in new places when you know where kind of everything's in flux at once. But yeah, we definitely see different patterns in different geographies.
Sounds good. Sounds good. Normally we try to keep these things to an hour, but I'm actually going to keep going for a little bit longer, if that's okay, Rob. We've still got over 100 people online listening along, and there's a few other questions, so we'll try and get through a few more if that's okay with you.
Sure. Yeah.
Another question that we have here from Michael Davis. What technology do you use for your feature store, feature collections? Have you built something internally, or do you use a product?
So it's, I believe, so I'm not quite sure if the question's referring to, so I think probably I'm not the right person to answer this question. We have built something internally, I think, as in there's an engineering team that deals with the back end of our feature store and our feature generation process. But I'm not sure exactly the combination of open source libraries and so on that have been put together to do that. So yeah, I think I probably can't answer that question very well, unless I don't think I can answer that question very well.
Follow up direct, Rob. I'm sure we'll worry about that one after. Perfect. Thank you. I'm going to skip on to the question from Josh now. Josh was asking, is there a specific reason why first order Markov chain rather than higher order is chosen?
So I think first order, I think probably just for simplicity and proof of concept purposes, we can see, like, obviously first order simplest. So I am not super familiar with it, but I assume higher order is kind of saying that it's not just each event is not just dependent on the previous event, but has dependencies that go back further, right? And clearly you would expect that would improve performance, and it's something we talked about looking into more, but it's just simplicity basically.
Perfect, thank you. I'm going to take the question here from Andrew Oates. It's probably relevant to a number of different industries actually, so it'd be interesting to hear how you answer this one. But Andrew is saying, great presentation, Rob. How does the balance between speed and quality of decision factor into your model evaluation?
So I guess it's one of those things where there are certain, I mentioned, I guess, the theme of the presentation, which was like friction-free online retailing, and one of the types of friction that online retailers really care about is the speed of the transaction, how long customers are left hanging around. So speed of decision is important to our customers, and there are some industries where it's particularly important, and we have tighter latency requirements. So we do end up building models to a latency constraint sometimes. And typically our biggest latency constraints are like in the third-party querying we do. So if we have to query a third-party database to get some piece of information, that's typically where our largest gains of latency are. So basically we have some different models where we use different sets of third parties, and then we can kind of clearly see this model has basket 1 of third parties, model has basket 2 of third parties, and we see a 3% drop in loss rate. So then it's kind of like a commercial decision, like 3% increase in loss rate, say, for the one with less third parties. So then it's kind of it's part of the whole commercial negotiation, I guess, is well, we can meet your latency requirement, but it's a bit painful for us, so we can't do it at that rate, and so on. So it's all part of that, I guess, that commercial structure of the relationship with the retailers, to make sure that it's a virtuous circle where all partners in the relationship are getting something from it. Like so that's kind of where it comes down to.
Perfect. Thank you very much. I'm going to take two more questions, I think, and then we'll draw things to a close. There's a few people asking about the recordings for the talk. The talk is recorded. There is a small paywall just to pay for the platform to access the recordings. If you would like the recordings for free, there is the option to share a post on LinkedIn about the FinTech month, tag the Data Science Festival. We'll be able to sort you out with a coupon code for that one. So you will be able to watch it back. I think there's a few people keen to watch this on repeat, Rob. In terms of the last couple of questions, I'm going to go to the question there from Neil Whitfield. I guess, you know, it'd be rude not to have one COVID-related question, wouldn't it? You know, it's been a while. Neil's asking, how have you dealt with transaction data changes caused by various COVID-related lockdowns? I mean, do you notice big differences? Does it immediately impact your models? Do you have to adapt?
Yeah, so it was fascinating actually about this time last year when we were all, you know, sitting at home, wondering if the world was going to end around us, and watching the changes in our data. It really was like in, you know, a few weeks, we saw the growth, the overall volume growth that we had planned for and expected for in sort of 5 years or so. And I think for the most part, I think data science got the easy end of that problem, because in the most part, it was, you know, genuine traffic was growing much quicker than fraud was, because it was suddenly everyone no longer going to shops and ordering stuff. It was, but we have seen some increases in certain fraud patterns, particularly kind of what we call mule fraud. So this is people get recruited they think they're being recruited for a job. Like you get an email saying, would you like to be an Amazon quality control worker? We'll pay you $50 a day. We'll just send a parcel to you and you just forward it to this address, things like that. That's gone up a lot because it's much easier to recruit people for that now, because there's lots of people stuck at home. But yeah, I think in general, the data changes from our point of view, it hasn't mattered too much. We've always dealt with spikes in traffic before with promotional periods and around kind of you know, Black Friday sales and stuff like that. So it was kind of just like that, but for a month. I think the people who felt the heat a bit more were the infrastructure and engineering teams, who suddenly having to deal with Christmas every day of the year. But luckily, you know, most of our infrastructure is all cloud-based, so I think we were able to scale easily enough.
Turn on some more machines.
Yeah.
Okay, I'm going to shoot down towards the bottom. There's a question that's come in from Doug, and it was one that I think we were talking about in the green room before we started the webinar. Essentially, Doug's asking, you know, do you have one model for all transactions, or do you have many specialist models? Is there benefit in putting vendor-specific or sector-specific features into models?
Yeah, it's a good question. I think our aim, or one of our aims is to try and have as few models as possible, because every time you keep adding models, you're multiplying all of your model curation and jobs that you're going to have to do down the line, and monitoring and all this stuff. So in general, we try and have fewer models, and so most traffic just goes to our general model. But we do have a few specific models for certain basically certain big retailers. If their traffic is very different from what we call a general traffic, in, you know, either in geography or sort of the risk factor of their products, or they have very specific integration with us, so they don't send us some crucial data or something like that. And typically, if they're very high volume, you know, if they were 10% of our total traffic, then the fact that then they would sort of have a material impact on the training of our general model if we kept them in the main traffic. And also, if you know, if they're 10% of our traffic, and they only sell high-end electronics that's very risky, then that kind of skews the model's perception of what normal risk is and stuff. So yeah, we do have several different models, but it's to give you a sort of order of magnitude, it's in the tens, not the hundreds or thousands or anything.
Perfect. Thank you very much, Rob. I'm just going to start to bring stuff to a close. There's stacks of questions that we haven't had time to get to. So thank you for asking those questions, and hopefully in future webinars we'll get the chance to get to yours. call out a few of the messages that come in: Gary, Vivek, Rory, Mika, Syed, Sana, Ina, David, Nabi, Neil. The list goes on and on. So thank you all for saying thank you to Rob. It is worth just having a quick scroll there, Rob, to feel the love before we end things. But
thank you, everyone.
Clearly,
thank you for listening.
Very popular webinar. I just wanted to call out a thank you to Signifyd as well. Been an absolutely fantastic partner in terms of supporting the FinTech Month. It's been really interesting learning more about your business, and definitely look forward to seeing where you guys go over the next 12 months or so. And hopefully we may even get the chance to get you back and do perhaps even a deeper dive, or see what you've been working on towards the end of the year or something like that. So yeah, I'm just going to wrap things up now. Thank you, everyone around the world for joining us. It's great to have you with us. And I'm just going to end by thanking you again, Rob, for giving up your time and coming to share with the community. I hope you've enjoyed it.
Yeah, thank you, everyone. Bye.
Perfect. See you all soon. See you next week. Bye-bye.